connect a file descriptor in user space to a network interface in the kernel. The difference between them is that if you have a ton device, you read and write IP packets. If you have a tab device, you read and write raw Ethernet packets. And this is used by virtualization for, QEMU, for instance, will create a tab device, launch the VM. It will attach the kernel network side to its imaginary local network, which we'll get to later, and then it uses the user space side to emulate a network card for the virtual machine. So you can see here we have our computer running virtual machines. Each one has a tap device which connects directly to the real kernel. And with containers, we tend to use veth pairs. So veth is a virtual Ethernet interface. When you create one with IP link, it actually creates a pair of interfaces rather than only one, like with the tunnel device. And those two interfaces are a tunnel so that any packet that goes into one of them comes out the other one and vice versa. Normally that would be completely useless, but with containers you can move one side of the tunnel into a different network namespace in a container, and then you basically have a tunnel from inside the container to outside into the main network namespace. The third possibility for an imaginary network card is to actually use a real network card. You can assign a real network card directly to a virtual machine or container. If you're using virtualization, there are CPU extensions like VT-D that allow you to have the virtual machine directly talk to your PCI card or whatever. If you're using containers, you can just move your real Ethernet card into the network namespace just like you would do with a veth pair, and then the container can access it. The problem with this is that you probably have more virtual machines than you have network cards. So they came up with something called single root I/O virtualization, where if you have a very expensive network card, it can pretend to be multiple virtual network cards. And then you can assign, usually it's either 16 or 64. So you can then assign one of the virtual network cards to each virtual machine or container. Mostly virtual machines. People aren't really using this with containers yet, or much. And then each of those virtual network cards essentially connects directly to the physical Ethernet without going through the kernel or hypervisor or anything else, which on the one hand is efficient. On the other hand, it means that you can't do extra firewalling or filtering on that card. So it's only useful in a situation where you want the virtual machine to have complete access to the local network. Okay, so we have an imaginary computer with an imaginary network card. Now we need to be able to talk to other imaginary computers. There are two basic ways that people do this, using Linux bridges, which is the more basic, the older technology, or using vSwitch. Either way, the idea is basically the same. You have a bunch of VMs or a bunch of containers, and they're all connected to a bridge, which lets them talk to each other, and possibly the bridge is connected to the outside world somehow. So with Linux bridges, and I say Linux bridges just to differentiate them from hardware bridges or vSwitch or anything like that. It's just a simple network switch in the kernel. You attach network interfaces to it, and they're called ports. And then the kernel deals with routing traffic between the different ports. You can add a real Ethernet interface to your bridge as well if you want external connectivity. Sometimes instead of doing that, people will just use NAT and use IP tables rules to connect the bridge to the external Ethernet device. That's the default behavior for virtual machines with libvirt a lot of the time, just because it requires less configuration. You can use IP tables to a limited extent to control the flow of traffic along the bridge, but for the most part, the traffic just flows freely. Every machine can talk to every other machine. If you want to do more complicated things, you can use something like OpenVSwitch. OpenVSwitch is a combined user space and kernel network switch. You can program it using a language called OpenFlow, which lets you control the traffic flow. There's an example OpenFlow rule here. I'll be talking more about that a little bit later, so the details don't matter. But you can see this one is routing IP packets that are going to a certain network and does a bunch of stuff with them, and then eventually outputs it to port 1 at the end there. So OpenVSwitch has both the user space component and a kernel component. The user space part manages the database of all the rules and interprets the rules when new traffic comes in. The kernel part routes traffic more quickly once the userland part has already figured out where the packet should go, matching a given rule. OK, so we have an imaginary network on the local machine. We want to connect to other machines so that you can have a whole cluster of computers running virtual machines or containers and have them all talking to each other. There are a handful of protocols. Actually, there are a zillion protocols. Everyone keeps coming up with their own new protocol for doing this. One of the most popular right now is VXLAN, the Virtual Extensible LAN. It allows you to take arbitrary Ethernet packets, it wraps them up in a UDP packet, and then you can just send them to any other computer. Each packet also has a 24-bit, what they call virtual network identifier, so that which works like VLAN identifiers, so that you can have different flows of traffic all using the same VXLAN tunnel. In OpenShift, we use that to do isolation between containers that are owned by different projects. We assign different VNIDs to them, and then use that to control which traffic can go into which containers on the other side. So one problem with doing this is that because you have an inner packet and an outer packet, you need two different checksums, or two different sets of checksums on it, both the inner Ethernet and IP packet and the outer Ethernet and IP packet. And so hardware cards that do checksum offloading initially could not deal with that. They could do one set of checksums, but not the other one. And so you ended up losing a lot of performance on your network. Newer Ethernet cards now have special handling for VXLAN to get that back. Before people started making network cards that supported, sorry, no, this is not checksum offloading, this is TCP segment offloading. So another thing that some network cards do is they can automatically do TCP segmentation for you. So when you send big packets, it will break it up for you and rechecksum them and all that. Again, encapsulation like VXLAN breaks that. VMware came up with something called stateless transport tunneling, where they wrap the packets inside other packets that look like they're TCP packets, even though they aren't really. And then the network card gets fooled into doing TCP segmentation offload for it automatically. No one other than VMware really uses this, though. Microsoft, meanwhile, is using NVGRE, which is an extension to the GRE tunneling protocol. Again, it has a 24-bit identifier. Everyone seems to have pretty much settled on 24-bit identifiers. It's used by Microsoft. Of course, we all know what happens when you have multiple competing standards. So now there's a standard called Geneve, Generic Network Virtualization, which is mostly the same as VXLAN, except they've now added variable length extensible headers. Everyone seems convinced that we're going to need these at some point. I haven't actually seen any examples of what it will be used for, but everyone agrees we want to have extensions. It's designed so that the routers don't need to understand the extensions and can still pass on the packets, and you can still have hardware that will deal with the checksum offloading without understanding all of the extensions. And there is hardware that does that already, even though no one is really using it yet. But but everyone is sure that we're going to be using it at some point. So at the moment, OpenShift, OpenStack, various other things are using vSwitch for their local network, and then VXLAN for connectivity between different computers. Everyone is doing it slightly differently with their own set of rules. So the vSwitch people are now working on something called OVN, Open Virtual Network, which will provide a generic implementation of this that hopefully everyone can use. It's going to use Geneve. I'm not sure exactly how close to done it is. And then there are all these other projects. Weave and Flannel were both created for use with Kubernetes, which is Google's container orchestration system, which OpenShift is built on top of. Calico and Contrail are other projects. Neutron is OpenStack's networking layer. It has its own architecture, but then has plugins within that, so you can have an vSwitch plugin or a Calico plugin or a Contrail plugin. Eventually, they decided that there were too many plugins, so they came up with the modular that should be modular, not module. Modular Layer 2 plugin, which sort of encapsulates the ideas that were common to all of their plugins, and then it has plugins inside it. So it's a plugin that has plugins. But it's currently the recommended networking plugin for OpenStack. So OpenShift, as I said, is an orchestration framework for containers. It's built on top of Kubernetes, which is Google's basic orchestration system, which in turn is built on top of Docker, which is the system for running containers on a single local machine, but doesn't worry as much about the problem of multiple containers on multiple machines. OpenShift uses a networking implementation called OpenShift SDN that, like I said before, uses vSwitch and VXLAN. Initially, the OpenShift SDN implementation allowed all containers to talk to all other containers. The more recent version of it is multi-tenant, which means that each project, which is an OpenShift concept for dividing up the containers, each project has its own ID, which then gets used on the VXLAN and in the OpenFlow rules so that different projects can't talk to containers in other projects, and therefore you can have a single OpenShift cluster with multiple customers that don't necessarily trust each other, and all of their traffic is kept separate. So it uses vSwitch, which uses OpenFlow rules, and this is sort of an example of some of the kinds of rules that it uses. So, okay, that's not really that visible. Traffic coming out of a container here, you see we match in port, which identifies which port or which interface the traffic is coming in from. We check that it has the right source address to make sure that people aren't spoofing and are using the IP address that we expect them to. This load instruction here sets a register to this value, which is the tenant ID or network ID for this particular container. And then go-to table tells it to go to a different table within the OpenFlow rules where more rules get processed. Later on, we have this rule which directs traffic to another node. So it's saying if you have IP traffic which is destined for any of these IP addresses in this network range, then, and again, so there's this rule that moves the network ID into the tunnel ID field, sets the tunnel destination to the IP address of the other host where this virtual network is hosted, and then outputs it on port 1, which happens to be the VXLAN port. And then as traffic arrives coming in port 1, we go to another table where we verify that it has the right destination, load the tunnel ID into register 0, go to a different table. Eventually, we get to the table where we match on the container IP address and match that the tunnel ID is what we expect it to, and if it does, then we output it on the right port. And it goes to the container. For a lot more details on how OpenShift networking works, there's another talk later today, Networking in a Container World. Rajat Chopra, who is up there. And that is at 4:30 downstairs from here. And that is all I have. People have questions? Hopefully. Yes. You don't count. You're my boss.
Is there a drive to make the syntax simpler? Because that was way too complicated for any non-expert.
So he's asking, is there a drive to make the syntax simpler because this is way too complicated? You can use simple syntax if you want to do simple things, I guess. It makes sense once you learn it all. It's pretty simple. There are different criteria that you can match on here. We're matching IP packets. This is the source, network source. So no, OpenFlow is a standard. It's not only used by vSwitch, it's also actually used by some hardware routers. And it's actually being extended with more syntax and more different possibilities. So, yep.
Have you done any work with external OpenFlow controllers, controlling the container networking?
So the question is, have we done any work with external OpenFlow routers or repeaters talking to the containers? No. So Calico uses GMP or BGP, thank you, to control routing tables on routers. But yeah, I mean, if we were going to use OpenFlow to talk to external repeaters, then that would limit what sort of hardware people could use OpenShift with. And so we're not worrying about that. We're just assuming IP connectivity between the different hosts holding the containers.
So you're using things like table 5, output 1, and that kind of stuff. Is there any way to parameterize those things or use in a way that you have to design your whole solution, right? Those tables with
So he's saying, is there a way to not have all of these hard-coded magic numbers like import 5 and output 1 and table 5 and all of that? The answer is no. Although I've been thinking about at least making it so internally when we're referring to all the rules inside OpenShift to have something that lets you substitute in variable names or something, and then it will just translate those to the raw numbers before passing it to OVS, OF control. Mm-hmm. Okay, what happens when I missed the very beginning?
Yeah, what happens when you add a new node, for example, to OpenShift cluster? Like a new node with IP.
Okay, so you're saying what happens when you add a new node to the OpenShift cluster? Each node listens for notifications from the OpenShift master, and when it sees that a new node has been added, it will add new rules like this one. Basically, there's one of these rules for each node, so that it knows which subnet which container subnet is on which node, and then it has to add a rule for each one. Sorry?
It's done all the rule updates are done automatically by OpenShift master.
The master tells the nodes when a new node has been created, and then each node adds a rule to its own local vSwitch database. I'm supposed to be throwing scarves at people. But they don't really throw very well, so let me try tying it in a knot.
We are going to build a solution based on the OpenShift with the multiple nodes located around the world.
Sorry, with the multiple.
With the multiple nodes located around the world in the different data centers. And we would like to connect the open vSwitches with some kind of technology. Well, we would like to do routing between them, but establish some kind of tunnels. We are experimenting with GRI, but it's not secured. Can you recommend any other solution?
Okay, so you're asking about security specifically?
No, I would like to ask you which technology would you recommend to use for connecting the open switches for long distances?
Okay, so what technology would we recommend for connecting open vSwitches between long distances? So the nice thing about VXLAN as opposed to something like VLAN is that it's a layer 3. So as long as you have IP connectivity between the different OpenShift nodes, they can send packets to each other. VXLAN is not encrypted. So there are people who are looking at using IPsec and then sending the VXLAN packets over an IPsec tunnel. We don't have any support for configuring that automatically, but it's definitely something that we're looking at. For now, it's generally assumed that all of the nodes are within, on the same network basically, and that you more or less trust that network. Or you have some sort of VPN or something connecting your different data centers so that the packets get encrypted by that.
Something like VXLAN over IPsec or something like this.
Yeah.
Thank you.
Okay, and do you have any plan to create some, because we have a vSwitch, and as I remember you said that the problem is that you still need to have a properly configured IP networking, yes? And do you plan creating some virtual routers or distributed routers for vSwitch or virtual firewall? Because it's the tendency, for example, Cisco company create some virtual network that also optimize and accelerate the traffic between separate container or virtual machine on different hosts, and you can easily manage. Now we have still the problem that you need to a network guy that will create all the network stuff between the computers, yes?
Mm-hmm.
Is there any plan to add, I don't know, virtual routers or virtual firewalls that will be supported with OpenShift or something like that?
At the moment, the plan with OpenShift, okay, so the question is if we have plans for more security or other fast connectivity, whatever stuff between OpenShift nodes. At the moment, we're just working on the simple case, basically. But OpenShift is built on top of Kubernetes, which has its own network plugin system, and so people will be able to write other network plugins that they can substitute in. There are people who we're working with who are creating more complicated, or systems that plug into their own networking infrastructure. I'm not sure if Cisco is one of them or not. But.
Yeah.
Mm-hmm. Oh.
I have a question I don't want to start. So basically I've been working with Open vSwitch, and so there is a lot of this stuff that there is Open vSwitch inside OpenShift, like OpenShift inside OpenStack. So with each of those, the MTU drops and drops and drops. So
yes.
Is there any mechanism or something in the works to automatically detect? Because I had really problems with MTU when it sets the MTU to something that's higher than the MTU on the lower layer, and it drops big packets.
So the question is about using OpenShift inside OpenStack and problems with MTU and stuff like that. So one way that people are deploying OpenShift is on OpenStack-based clouds. So you have your OpenStack with its Open vSwitch and tunnels, and then OpenShift running on the virtual machines with its tunnels, and so its tunnels are going through OpenStack's tunnels, and you lose a little bit of MTU at each step, not to mention that it's horribly inefficient. we have a Trello card open about creating a network plugin where essentially OpenShift would be aware of OpenStack's networking so that you could avoid having the double tunneling. But yeah, it's not something that we're actively working on at the moment, but it's something that we know should be addressed.
Okay, thank you.
Last year, you guys showed like a visualization tool that depicted the connections. Does that work with all these layers? And
So that's plotnet CFG. The question is, so we have this tool, plotnet CFG, that graphs complicated networking configurations with bridges and tunnels and all of that stuff. Rashid, it doesn't actually look at OpenFlow rules, right?
It doesn't look at flow, but it looks at all the native.
Right. So it can plot the sort of. So it can plot like at this level where it can say, yeah, you have these containers and they're connected to this bridge, and the bridge is connected to the Ethernet and all of that. It doesn't recognize the flow rules, so it wouldn't be able to say, well, the WordPress container can talk to the Rails container, but not the Apache container, because it doesn't know anything about the.
But the plan actually is to add these supports in the future.
Well, there you go. The author of plotnet CFG says that there's a plan to add that in the future, although, I mean, that would require parsing arbitrary rules, and I guess I could just know OpenShift's rules specifically.
We have a Trello card.
Or maybe when everybody moves to OVN, that will solve that problem. Anyone else? Questions? I still have one scarf to get rid of. Okay. Oh, do we support IPv6? Do we support IPv6? No, at the moment, Docker supports IPv6, but Kubernetes does not. And the issue is if we wanted to support just IPv6, it would probably be pretty easy, but supporting IPv6 most likely means supporting dual stack, and so you need to add a second IP address field to all these different data structures. So again, we have a Trello card. Trello is the system that we use for tracking all of our work on OpenShift. Yep.
How do you integrate with DNS? Because when you have multiple containers, I assume that you are not addressing them only by IP address, right?
So Docker and Kubernetes both have their own solutions for this involving what they call services. And so in OpenShift in particular, there's a SkyDNS pod that knows about all of the services, and so you can look up the services by name, and it will resolve to the right IP addresses. Oh, sorry, and I should have repeated. The question was, how do we deal with DNS? Because obviously these containers can't all be referring to each other by IP address. Okay, that's it.
well.